Hello students, in this module we will start doing the performance analysis of direct sequence spread spectrum systems in presence of tone jamming. By the term tone jamming, I mean to say that in the RF carrier frequency, the jamming signal is present in one of the RF carrier frequencies, and the analysis will be going on in the continuing modules when the presence of this jamming signal will be exactly on the carrier frequency of your interest and maybe close to the transmission frequency of your interest, RF carrier frequency of your interest, or and also on the distribution of this jamming signal. We will start today with the in general format and the general framing up of the general mathematical frame format of this error probability calculation, mainly in presence of the jamming signal, and then we will keep on adding one by one the typical characteristics of the jamming signal. Let us refer this known block diagram of matched filter based receiver architecture for direct sequence spread spectrum communication. We have referred this block diagram earlier also. Hope you will remember. I am repeating once again the block diagram architecture that we have learnt earlier for PSK, coherent PSK communication. RT was the received signal at the receiver front end. RT was modeled as the intended signal transmitted added with the interfering signal or the jamming signal, and this is a noise signal. So, this combined signal of intended clubbed with the interference as well as AWGN noise has entered into the front end of the receiver. Receiver has synchronized it to the carrier frequency FC, and next chip matched filter is matched, its transfer function is matched with the chip waveform psi t. So, it should be its function will be psi of minus t. The sampler is running at the chip rate. Next, after the match filter output, the target of the sampler is to produce G number of the samples, where the G will be symbol duration to the chip duration, the number of the chips present per symbol duration, and it should be exactly with the G to for the next adder circuit to work upon it. The demodulated sequence here obtained here, I mean the G number of the samples, will be now dispread with the locally generated spreading sequence, and here the samples that we will get after dispreading, I denote it by Zi. Such Zi samples after the total mechanism of the dispreading occurs by this multiplication and this addition finally. So, the samples that we are getting after the immediate multiplication by the spreading sequence is denoted as Zi, and after that after adder, the signal that is entering into the decision device for taking the decision about the message signal transmitted is written as V. We will actually start our analysis from this Zi, then we will try to find out the expression for this V, so that the decision device output whatever we are getting will be utilized for the error probability calculation. So, we will vary the structure of this IT from module to module from now onwards. Let us first see how this error probability framework can be obtained. So, as we understand, and I have mentioned that the chip matched filter is already matched with the impulse response, its impulse response is psi of minus t, it is matched with the chip waveform. Let us consider that we have transmitted dt is equal to d0. So, we understand that transmitted signal can be either d0 or d1 corresponding to the message signal of 0 and 1, message bits of 0 and 1, and this d0 is transmitted over the symbol duration of Ts, and hence then the demodulated sequence Zi. Where did we get this Zi? Zi is input of this adder, and it is also the output of this modulated signal multiplied with the locally generated spreading sequence. Hence, we will get our input was RT and the psi t minus ITC, it is actually the locally generated sequence, and these are getting multiplied. So, we are ending up with this with the cos 2 pi f c t, it was there with multiplied with this R t beginning of the match filter to bring it down to the baseband. And this integration with this, as it is we are interested on the ith chip. So, the integration is running over one chip interval. Let us assume that it is the ith chip. So, the duration will be ITC to I plus 1 TC. Remember, this RT is a combination of, as I have told earlier, that it is a combination of the intended signal plus the interference, this is the jamming signal, and also the noise. So, obviously, this integration will have three parts. The part contributing to the intended signal will be ST psi t minus ITC and cos 2 pi f c t dt, which we will mention here now SI. IT into psi t minus ITC cos 2 pi f c t will be the contribution from the jamming part, and NT into cos 2 pi f c t will be the contribution for the noise part. So, finally, this whole expression or the Zi can be expressed in terms of Si plus Zi plus Ni, and this I is varying from G to capital G and G minus 1, because we have total G number of the samples in hand. And remember, when we will compute these individual integrations, target is to find out the variance and the mean and variance of each of these parts in order to find out final EB by the signal power to the noise power. So, that we can utilize that SNR in the computation of the symbol error probability. And in order to proceed, when we are computing this integration of the first one, equation 1.9, remember that this frequency f c, which is the carrier frequency of your transmission, this f c is considered here to be too high compared to the frequency of the chip. So, the rate of the compared to the rate of the chip, our transmission carrier frequency is too high, such that the higher frequency terms of the cos, which is coming when we are solving this integration, can be avoided. If we proceed little bit by avoiding that higher order terms, we will be ending up with this pi d0 square root of s by 2 t c, and this expression we have also seen earlier, and I have explained about how did we arrive this pi into d0 square root of s by 2 t c in the some of the earlier module. So, we will proceed with the consideration that this integration will boil down to pi into d0, where your pi is the value of the ith chip, d0 was the transmitted signal, s is the power associated with the transmitted signal, tc is the chip duration. And with this understanding, in the next slide we will try to see that what will happen now if this interference IT, tone interference IT is exactly coinciding on the transmission frequency of our interest, which is equal to f c. So, what we said is, we said that now this J I, which is actually getting we are getting from the contribution of IT, this IT we are trying to see that what will be the effect, how to compute the power of this section if IT is exactly coinciding with f c. So, IT is such that Zamar could locate your transmission frequency, and exactly on the f c he has designed his signal. If that design is possible, how IT will look like? IT will look like the equation 1.20. So, it is having his average power called I, and it is having the carrier frequency of transmission exactly same with our intended frequency of transmission, and phi is the relative, the phase associated with signal IT, which is relative to the desired signal. So, it is having some phase offset with respect to the desired signal, denoted as phi. So, if this is the situation, and if the assumption holds good that the carrier frequency transmission is too high than the chip rate, then we can now compute Ji of the earlier equation that I have shown in the earlier slide by substituting the value of IT from this equation 1.20. And remember one more thing, that the signal that was entering output of this adder, if you go back and check the block diagram I have shown earlier, there was an adder that is adding over g number of the samples, and then output of the adder was entering into the decision device. I wrote in the front that the input to that device is decision device dd is V. This V is also having 3 components, because we have seen that the Zi is having 3 components, Si plus Ji plus capital Ni. So, interference, signal and the noise. So, here also we will be able to see 3 components. One contribution will be there from the intended signal part, and another contribution will be from the jamming part, which we are defining as V1, and the third contribution will be from the noise part, which we will be defining as V2. So, once we are able to calculate this integration of Zi, so V1 here will be nothing but the sum of all them multiplied with the corresponding Pi values, because we understand that once in the Zi component, all the IT is now spread by this spreading sequence, locally generated spreading sequence. So, when this addition will go on, all the corresponding values of that sample should be multiplied with the Ji. So, if I do this substitution and continue the integration, we will be ending up with the equation 1.21, where actually some change of the variables will be definitely required to come here, because the substitution instead of ITC to I plus 1 TC, we have done it over the 0 to TC. So, that shifting of the change of the variables is essential. And finally, the V1, first you please substitute the value of IT in the examples of in the expression of the Ji, and then you add them up. So, finally, we will be coming up with V1 with this expression, where you have utilized the, after substitution we have utilized the fundamental of the trigonometry by taking 2 cos A cos B. This will be the cos A and this is the cos B section. So, 2 cos A cos B will lead you cos A plus B into cos A minus B, and then finally, we will be ending up with this, because we understand that cos of A plus B is giving a very higher order terms, and we are not ready to accept all that. And inside this expression, we know that this psi t is the cheap waveform, Pi is having values of either plus 1 or minus 1, phi is the relative phase of the interfering signal with respect to the desired signal, and Tc is the cheap duration, I is the average power of the jamming signal. Once we have calculated Vi, then we understand that the shape of the waveform that we have considered here for the chip design for the spreading sequence, we consider since beginning that there are 2 different kind of the chip waveforms are possible in our consideration. One is the rectangular chip waveform, another is the sinusoidal chip waveform. For rectangular chip waveform, we know that the waveform will be having a value of 1 within the, from when the t will be varying from 0 to the capital T, and otherwise it will be 0. Whereas, the sinusoidal chip waveform will look like this. And let us also consider that out of this g number of the samples that the sampler has given us, let us consider that for k1 number of the chips, the value of the chips are equal to plus 1. For k1 number of the chips, the value of the chips are plus 1, that means the value of the Pi in the earlier equation you can put equal to 1. And hence, for the rest number of the chips, which is given by g minus k1, you will get the value of these chips equal to minus 1. With this consideration, and if I substitute the value in the earlier slide, here if I substitute the value. So, now what is the substitution going on? I will substitute the value of psi by the first by rectangular wave, then by the sinusoidal wave, and then I will substitute the value of the Pi by some expression, because the total number of the chips that I will get will be k1 plus g minus k1 actually, and then k1 g minus k1 plus actually your k1 will be the total number of the chips available. And if I keep on substituting all that, and finally, we will be converging to the equation given by 1.23. We have evaluated that integration there. Remember this 2k minus 2k1 minus g is the contribution of the total number of the chips that you are having, and this kappa is a new term introduced in this expression because we wanted to keep the effect of both the waveforms, rectangular and sinusoidal chip, by some common factor. If you put if you consider for a rectangular chip, then this value of the kappa will be 1 and the expression will boil down to square root of y by 2 and Tc 2k minus 1 g into cos phi. But for the sinusoidal chip, the value of the kappa will be 8 by pi square. So, good part to observe here is if I choose a sinusoidal chip, then it is true that the contribution of the V1 will be some amount down, and if I calculate that in terms of the dB, you will get 0.91 dB gain against the tone interference which is designed by the rectangular chip. So, if you are a jammer and you are designing your signal, and if you consider the signal to be spread by the rectangular chip or by the sinusoidal chip. So, if we actually sitting in the intended receiver, you design the chip waveform by sinusoidal chip. So, it is expected that the effect of the jamming can be actually 8 by pi square or 0.91 dB down. So, you will get an additive advantage of 1 dB around over the rectangular chip design. So, by designing the chip, choosing the chip waveform, you can have a gain over the jammers. You have a gain over the jamming signal or jamming interference due to the jamming compared to the rectangular chip. Another important observation is, if my k1 is equal to, if I choose k1 equal to say half, so sorry, k1 is equal to g by 2, then this contribution whole V1 will boil down to 0. So, if you choose the sequence in such a way that half of the time the sequence is giving you plus 1 and half of the time the sequence will be minus 1. So, if you are having a even length sequence and if you are having half of the sequence values is always plus 1, half of the total half of the sequence values is equal to minus 1. So, your interference will be 0. So, when you are designing the code for your spreading code for your you are choosing the spreading code for your design. So, keep it in your mind. So, one is related to the number of the plus 1 and the minus 1 that should be in the codes to minimize the effect of the interference, and also what should be the choice of the shity, I mean the choice of the pulse shape that you should be considering in the code design itself. So, in the both way, this equation give you the indication how actually you can minimize the effect of the jamming signal in the receiver. So, code and the chip waveform for that code plays very important role in this regard. So, coming back again, so if the random binary sequence we are considering for this sequence design, so we understand that pi will be equally likely to be plus 1 and minus 1. And in such a situation, the conditional symbol error probability can be given by equation 1.25, where actually this conditional error probability is also the combination of a conditional symbol error probability when your k1 is given k1 number of the times you are transmitting the symbol to be plus 1, and given the value of the phi and given the data symbol to be either plus 1 and minus 1 if they are equally probable. So, it should be the conditional symbol error probability will be the combination of the both the conditions when your symbol error probability will be, the conditional symbol error probability will be half of the times equal to plus 1 governed by plus 1 transmission and half of the time will be governed by the minus 1 transmission. We can actually compute each of their value and then take the effect of the combined effect of both the situation to compute this PS phi. Remember one thing, once we are considering that situation of equiprobable case, in such situation this V1 is approximately constant, and hence if I go back and see the input condition of the decision device V, which is a combination of the known sequence, contribution from the known sequence, mean value of the known sequence part, and mean value of the V1 plus the mean value of the V2 constituting the mean of this V. Then we can see that this guy will have a Gaussian distribution now, because this is almost deterministic, and V1 is a constant and V2 is additive, governed by the additive wide Gaussian noise. So, Gaussian process is associated with it. So, definitely the V will be now having some Gaussian distribution. And so, V2, the way V2 is will be expressed, similarly the way we express the jamming signal at the input of the decision device, following the same thing, it will be given by this. And this S we have understood is the signal power, and this is the symbol duration, and Ni is the noise component in the displayed signal. So, we can write down the V as like this, and if I take the consideration of 1.23, the equation we have explained last time. 1.23 is explaining about this D0 section, and also the V1 expression for the V1 is obtained from the 1.23. So, using the earlier fact that we have a contribution for the signal section like this given by 1.9, we have the contribution from the V1 given by this, and mean value of the noise is equal to 0. So, finally, the conditional expected value of this V, which is entering into the input to the decision device, will be given like 1.27. Basically, it is the addition of this signal section, mean value of the signal section, and the mean value of this V1. The variance equivalently like the mean, the variance of V will be also equivalent to the variance of all these three terms, and this is a constant part. So, its variance is having no effect, but finally, the variance of V will be contributed by the variance of both the noise as well as the interfering signal. We will see next. Remember, using that Gaussian density to evaluate each of the terms of this conditional error probabilities for transmission 1 and transmission of -1 will be given by this, where this S is energy part symbol, which is written by S into Ts, and this Q function is having a classical definition given in equation 1.29. Remember that once we are reaching here, so we will be knowing that typical value of the PS. So, that is a conditioned on the phi, conditioned on the Q1, and conditioned on the transmitted value D0. So, +1 and -1. So, what is the total symbol error probability now we are interested in? In order to compute the total symbol error probability, you have to know what is the distribution of this phi. See this, we should go back and we should revisit what was the definition of this phi. We defined in the first few slides that this phi is nothing but the phase associated with the jamming signal, and this will be given by the phase relative to the desired signal. So, this distribution of the phi for the sake of this mathematical analysis, and which is quite often true also, the consideration is valid that the consideration should be that phi is uniformly distributed, will be over a period of 0 to 2 pi. Definitely, it is a random variable and it will be uniformly distributed over a period of 0 to 2 pi. And we understand that cos phi will be periodic. It has a periodicity. So, we can give the final symbol error probability Ps equal to it is integration running over 0 to pi and this Ps phi. So, Ps phi is given by the equation here, where it is a function of the total number of the samples considered and also having the contribution for the conditional symbol error probabilities and for this we consider that both the sequences are equally probable. So, half of the times the contribution will be from the transmission of the signal 1 and half of the times the contribution will be signal of the -1. Please remember that both this conditional symbol error probability is heavily dependent on the choice of the k1 also. So, understanding the fact that you are properly choosing the value of the k1, such a way that actually that error probability I mean the viewer value of the V1 is not coming to 0 and he is contributing on the error probability calculation. We are coming here and finally, we have reached to the PS, equation of the PS, and substituting the value of this PS back to the equation of 1.25, we will be able to compute this PS phi, and now the total symbol error probability will be given by the final integration of this PS phi over a zone of 0 to pi. Because periodicity of the cos phi, there is no need to go ahead with this from 0 to 2 pi zone, and averaging over the pi out of that will be ending up with the computation of the symbol error probability. So, these equations and these considerations will be carried forwarded in the next two modules, where we will see that what will happen if we shift the carrier frequency, the jamming frequency close little bit from the targeted carrier frequency, but it will be close to the carrier frequency. What I mean to say is, you could assume what exactly is the carrier frequency as a jammer, but you could not exactly estimate the transmission frequency or carrier frequency of the intended signal, but you are very close to that. So, whether the consideration whatever we have seen in these expressions, whether how those expressions will keep on changing will be the consideration in the next module. Please remember, we will refer once again the equation 1.25, where we consider the PS phi and where the PS phi is based on the conditional symbol error probability. We will recall the pulse shapes here we have utilized to establish the expression, both the rectangular as well as the sinusoidal chip, and we will also recall the contribution of this symbol section on the whole computation of this computation of the V which is entering into the decision device, and the concept of this Q function and final symbol error probability in view of the different nature of the interference with different kind of the carrier frequencies will be continued in the next.